Lesson 2.1 is about if-then statements, which we call conditional statements. A conditional statement is something where the conclusion, what you're going to get at the end, is based on a certain condition. Like your friend says, if it rains after school, then I will give you a ride home. You'll get a ride home only if it rains after school, basically. We call the if part of it, it rains after school. That's the condition, actually. We call that the hypothesis, and then the conclusion is, I'll give you a ride home. So another example would be your dad says, if you get a B average, then you can get your driver's license. So your driver's license is conditioned on you getting a B average. And so we call those if-then statements or conditionals. So a conditional statement takes on the form if P, then Q. P represents the hypothesis. Q represents the conclusion. So if you get a B average, then you get your driver's license. The hypothesis was you get a B average. The conclusion is you get your driver's license. The words if and the words then are not, those are not included in the hypothesis or conclusion. So that would be the form of the original statement. Next, we have the converse of the original statement. And in the converse, we switch the hypothesis and conclusion. So if the original statement was if P, then Q, the converse to that statement would be if Q, then P, which says something oftentimes completely different than the original statement. In geometry, most of our theorems are stated as if-then statements. For example, if point B is between point A and point C, then the length of AB plus the length of BC equals the length of AC. And you know this is the segment addition postulate. Well, you will find that most of our postulates and theorems are stated in this form. So there's other forms that we can say a conditional statement in that are equivalent to if P, then Q. So the general form if P, then Q can be modified to say P implies Q, which is the same thing, meaning if P, then Q will follow. We could say P only if Q, and we could say Q if P. So the if P is still there. Basically, these all say the same thing. They say if you meet the condition specified by P, then definitely 100% Q will follow. Now, to disprove a conditional statement, if a conditional statement might be true, but in order to disprove it, you only have to show that it's false in one case. If it is not true 100% of the time, that is in fact not a true statement overall. So if you can find one counterexample, one example to show that where the hypothesis is true, the conclusion does not follow, then you can prove the original statement false. So let's look at a few examples of that. So here's some statements that are false and examples of a counterexample to prove the statement false. If you live in California, then you live in San Francisco. Well, that's not necessarily true. And so counterexamples to that would be you live in Danville or Alamo or Los Angeles or San Diego, any place that is in California but not in San Francisco. Another example, if points are coplanar, then they are collinear. Well, you could easily throw 3 golf balls on the ground and make them so that they are not collinear and show that they're all on the plane of the floor, but they are not collinear. If a line lies in a vertical plane, then the line is vertical. Well, no. You can, on a wall, draw a horizontal line across the wall, and there you have a horizontal line in a vertical plane, and that would be a counterexample to this statement. And then if x equals 49, I'm sorry, if x squared, that should say, if x squared, let me pen that in, if x squared equals 49, then x equals 7. Well, that's not necessarily true because x could be negative 7 for x squared to still equal 49. So all of those in red show counterexamples to the conditional statements. So the last thing that we're going to talk about is a biconditional. And a biconditional is a way that you link a conclusion and a hypothesis where the original statement is true and the converse is also true. In that case, you can link the P and the Q with the words if and only if, and that is what makes a biconditional. So, for example, if it says tomorrow is Saturday if and only if today is Friday. Now we could say if tomorrow is Saturday, then today is Friday, or the converse of that, if today is Friday, then tomorrow is Saturday. Because those are both true, we can link up the two statements with if and only if, and it doesn't matter which we put first, tomorrow is Saturday or today is Friday. I could easily switch those two, join them with the words if and only if, and it would form a biconditional statement. So that's it for if-then statements and the converse. We also learned about counterexamples and the biconditional statement.